Okay, so we're going to just talk about antennas and feed lines. And you'll see some weird antennas and some kind of typical ones. And part of it is also going to be, actually quite a bit going over standing wave ratio and how that's calculated and measured. So the first thing, get that kind of out of the way, is characteristic impedance. Any transmission line, which is basically any kind of cable, whether it's coax or what we call twin lead or parallel, where there's two wires and you have a current flowing through one conductor and back through the other conductor, is is basically a transmission line. And it will have different impedance depending on the spacing of the conductors, the diameter, things like that, and dielectric, uh, what separates them. Uh, so if we take a infinitely long length of whatever that is, and we measure it at one end, whatever impedance we see is going to be what's called the characteristic impedance. It also means that if you were to take a finite length, like a few feet or 100 feet, and you terminated one end in that characteristic impedance, that's what that's also what you would see if you measured the other end. And there's a formula you don't have to really remember, where that is the square root of the inductance and capacitance of the transmission line. Does that make sense? That's kind of a basic thing you need to understand.
So it's the square root of okay, the inductance over the capacitance.
Right?
Right. Okay.
That's how it's actually calculated. But usually, in the case of coax, when you buy it, it'll tell you what the characteristic impedance is, and also things like the velocity factor and the loss. And we'll talk about that uh, in a little bit, because transmission lines, whether they're coax or parallel lines, have loss, and loss goes up with frequency. Um, if it's a parallel line, the characteristic impedance is determined by the distance between the conductors and the radius or diameter of the conductors and whatever is separating them, called the dielectric. In a lot of cases with parallel lines, it's air, or it could be some plastic material that's a separator. And those values actually also allow you to calculate inductance and capacitance. Uh, but there's a formula for parallel lines where you have this constant, the 276 over the square root of the permittivity, which we call dielectric, times the log of the separation distance divided by the radius. Now, you're not going to have to do that formula. This shows you how it's calculated. And you can see if you increase the diameter of the conductors, the uh, impedance is going to increase. And if you increase, excuse me, if I increase the distance between them, it's going to increase. If I increase the radius or diameter, the impedance is going to decrease. So that's how they're able to manufacture it for a specific impedance. A typical one called window line, and I have a picture of it coming up, is 450 ohms. It's about an inch separation. We also use coaxial cable, and the formula is similar. Uh, the concept is a little bit different, and it's the log of the ratio of the inside of the shield divided by the diameter of the center conductor. So it's basically the spacing between the two conductors. This happens to be circular, which is why this 138 changes. Coaxial cable is typically going to be 50 ohms or 75 ohms. We use 50 ohms predominantly in amateur radio. You'll use 75 ohms in TV, going to your TV antenna if you have an external one, or connections to the monitor. Those are typically all 75 ohm coax. And I'm sure you're asking why we use 50 ohms. Is anybody asking that question?
Yep, indeed.
I thought it was the most stable.
Well, it turns out that back in the early days, this was kind of done by AT&T with long distance transmission lines. 30 ohms turned out to be the best impedance for power transmission. 75 turned out to have the lowest loss and is used by broadcast TV. So we decided, well, not me, amateur radio decided to kind of take an average. So they took an average of the mean and the median. And the mean is 52 and a half between 30 and 70. And the median is 47 and a half. And they average those, and it's approximately 50. So that's where it came from. Nothing magic. Antenna impedances will vary a lot. A basic half-wave dipole is approximately 72 ohms, and a quarter-wave vertical is approximately 35 ohms, because it's essentially half of a dipole. When we talk about using feed lines to an antenna, there's a phenomena called a mismatch where I might have a 50 ohm coaxial cable connected to a half-wave dipole, which is 72 ohms. So the impedances don't match. What happens is you get what's called a standing wave ratio, or a voltage standing wave ratio. And if you look at the animation, I'm assuming everybody's seeing these.
Yes.
The blue line is representing the signal that's being sent over the transmission line. When it gets to the antenna, because there's a mismatch, it's reflected in opposite polarity, 180 degrees out of phase. So that's the red line coming back. Now, at certain points, well, at all points, these are adding and subtracting, and you wind up with this black line, which is the result, which you can see is a much larger amplitude, still the same frequency, but it's going to have a much larger amplitude on the coaxial cable than the original signal or the reflection. And That's why it can create more loss because you have, you know, effectively more power at any point because you've got both waves. Um,
So does that create a hum or a feedback when it does that?
uh, well, indirectly, what it does, it causes um, the reflected signal to be coming back on the outside of the shield of the coax,
Right.
or as common mode on the parallel line, which will come into your shack and it's radiating. It may have a lot of energy depending on the amount of reflection. So it can cause what we call RFI. Uh, you might pick it up in speakers and things like that.
Mm-hmm.
Um, so you want to try to eliminate it, and we'll get to uh, things like common mode chokes later. And the whole purpose is to provide an impedance on the outside of the coax to block that current.
Right. So you can put a ferret on there and help.
Yes.
Yeah.
Or you can actually, depending on the frequency, for the higher frequencies, you could just loop the coax 3 or 4 or 5 times, which makes a coil or an inductor.
Okay.
And a lot of times that's enough.
Okay.
It depends, depends on the frequency. It's not going to work down at 160 meters unless you coiled, you know, 100 feet of it. But
Okay.
ferrites, or a ferrite large toroid that you wind the coax through 6 or 7 times. Okay, so what is standing wave ratio? Well, it's the ratio of the load to feed impedances. So in the case of the half wave dipole, let's say it's 75 ohms, it could be, varies a little bit. And 50 ohm coax, I'm going to have a 1.5 to 1 SWR. And if I measure it with an SWR meter, that's what I should see. Um, Depending on how long and how lossy the coax is. And we'll talk about that in a little bit.
I was going to just ask you a quick question because I currently have open coax cable from a satellite, which is 75. And I was told I could still use that. I would just have to modify how I used it so that it would be more, closer to 50. So I don't
Uh,
know what that entails, but that's what I was told.
okay, well, you could use it. Actually, it would be a better match to a half wave dipole, but you'd
Okay.
have to have a matching unit or quote tuner
Mm-hmm.
at your transceiver end to match it to 50 ohms, which is what your
Right.
transceiver wants.
Right.
But it could be a better setup because it's going to be maybe a little lower loss, but it's going to be you're not going to have as big a reflection coming back.
Okay.
In the case of where we're, say, connected to a half wave ground plane vertical, which is 35, we're going to have a 1.43 SWR. Now, these are normally enough that you can operate without having to do any kind of matching. It's not optimum, but you're not going to hurt anything. When you start getting up to 2 and above, you start running into problems. And at 3, most radios will actually do a foldback and reduce power, so you don't damage the output transistors. And of course, if we had a perfect 50 to 50 match, the SWR is going to be 1 to 1. You notice whichever way the ratio is, it's always the bigger number versus the smaller number. So they'll try to trick you on a couple questions with that.
Mm.
Um, You're probably familiar with old TV twin lead. It was 300 ohms. It's about a half, 5/8 of an inch wide. The ladder line or window line, like I said, is 450, and open wire is 600. You don't see that much of that. um, this is just a thing because there's a question about it. Um, there's some antennas like this non-resonant doublet, which we won't really talk about, which um, probably is going to give you a high SWR because it's very hard to match. So using a parallel transmission line like the window line or the ladder line uh, is going to have less loss. So you're not going to absorb as much of that reflected power in the transmission line, which in some cases could be enough to actually damage the transmission line. Here's some pictures of what we talked about. This is typical, well, twin lead. Some of it has little windows cut in it. Most of it I've seen has just been solid. Window line looks the same, except it's about an inch wide, so it's a higher impedance. And here's the 600 ohm ladder line, which just has spacers every so often to keep it apart. And it's like 3 or 4 inches apart. Okay, so we talked a little about a matching network, which we use to convert or match one impedance to another. There's basically 3 types of things we can use. One would be an LC network. It's typically going to be what we call a pi or a T network. And if you have a quote antenna tuner, which may be built into your radio or it may be external. If it's a manual one, you're going to have 3 knobs on it. And usually it's going to be what we call a pi network. So you'll have a capacitor across the input, a series inductor, and then another capacitor across the output. And all of those are variable. And normally the inductor will have taps on it, and you'll have a switch that you can select which tap or how much inductance. And then you have to rotate the variable capacitors to change the amount of capacitance. And you go through that process twiddling all 3 of those knobs to get the best match. Now in an auto tuner, it's basically the same thing, except it's done by a bunch of relays and separate capacitors and inductors. And the processor will just trial and error different combinations of capacitors and inductors to get the best match. And a lot of times, if it's quiet, you can actually hear it switching when it's trying to do that. You hear the little clicking. You can also use a quarter wave transmission line. I think I have an example of that one. And then a lot of times you'll use a balun or an unun. The difference is a balun means it's a balanced to unbalanced. An unun is an unbalanced to unbalanced transformer. So you use the impedance ratio of the transformer. And if you remember last week, we talked about that was the square of the turns ratio. So you try to wind a transformer that has the correct impedance ratio so you can match 50 ohms to whatever you're trying to get to. You typically see these on like an in-fed antenna because you're trying to match maybe as much as 5,000 ohms. It says it prevents standing waves by matching the feed point impedance to the feed line impedance. That's really only true if it's at the antenna. If it's down at the receiver end, it's not affecting the standing wave ratio that's on the feed line. And if it's at the receiving end, it will block the reflected power going to your receiver, but it's just going to be reflected back up to the antenna and then back down and then back up and then back down until it's all been dissipated. So we talked about what SWR was. It's just a measure of the impedance match, the ratio. Like I said, if you have a lossy transmission line, and all of it has some loss, but if you have one that's very lossy, if you have a very high SWR, it's going to increase the signal loss even more. And the higher the transmission line loss is, the SWR reading that you're going to see, whether it's on your radio or an external SWR power meter, is going to read lower than it really is. The reason, if you think about it, I put 100 watts out into the feed line, and I have a 3 dB loss going to the antenna. That's not actually unusual. At the higher frequencies with a long piece of coax, like 100 feet, you could easily have 3 dB loss. So that means I'm only getting 50 watts at the antenna. So if I had a perfect match, I wouldn't get a reflection, but I only have 50 watts at the antenna. If I had a mismatch of, say, an SWR of 2, then I'd be reflecting half of the power back. So I'm going to send 25 watts back. But I'm going to lose half of that on the way back because I got another 3 dB loss in the transmission line. So what I'm going to see is 12.5 watts reflected. So that's not going to look like a very bad SWR at all, where it's an SWR of 2 in reality. So you can't necessarily trust the reading you get on a SWR meter or by doing it with reflected and forward power at the receiving end, because it doesn't take into account the loss in the coax.
So what do you use instead of an SWR meter?
Well, I have an SWR power meter, and just that you can't believe, it's always going to have, or it's always going to read low. How low it reads is a function of the loss. So if you have a fairly good match to the antenna and low loss cable, it isn't a big issue. It's basically here because somebody decided it would make a good question.
Okay, good enough.
But
But
in
you're
reality,
looking for, I'm sorry, go ahead.
Go ahead.
I was gonna say but you're looking for 1-to-1, correct? So if your
Yeah,
load's
but
4-to-1 or 5-to-1, you're way off.
right. You want 1-to-1, but you'll never get 1-to-1 in the
Right.
real world. But you may get 1.10 something or 1.11.
Right. But your goal is to get as close as possible. So
Right,
the bottom two numbers are not even near what you would be
right.
satisfied with.
And but one thing it is telling you is how much reflected power you're actually getting back into your receiver and your transmitter.
Mm-hmm.
And that's one thing you care about because you want to make sure that's less than 3. So even though in reality at the antenna it might be an SWR of 5, uh, but it may only look like 3, and may really only be 3 at the receiving or transmitting end. And that's where you care about it. So you don't want to blow the transistors. Now, if it was a tube type uh, radio, it's not as big an issue. They handle SWR pretty well.
Okay, I have a quick question
Okay.
because this is the way yeah. Um, Looking at the bottom two, um, I guess formulas.
Uh-huh.
When you read that, it's reading 200 equals 50. But when you read the exact same way that it's written, it switched from 50 being the front number to 10 being the back number. Why? Why did that switch? Like, is that going to be relevant to me trying to locate something? Because I don't understand why the exact same formula switched the numbers.
Not sure I'm following you.
So 200, and I guess is it omega? I mean, what is that? I don't remember the sign.
Ohms.
Well,
Ohms.
that's an
Okay.
and sign. Okay.
Okay.
The
Okay.
load's 200.
Okay. So
The
200.
cable impedance ZO is 50
Okay. And then the way they wrote it out being SWR was 200 divided by
divided by
50.
50.
By 50. Now, if you go to the one right underneath it, it's the exact same thing. We have 10 ohms and the ZO equals 50, but yet we write it this way, 50 divided by 10. We swapped it for some reason, but it is exactly the same.
Right. Remember,
Why?
remember I said that there was some questions trying to trick you that we
Uh-huh.
always use the larger number
First.
relative to 1.
Yeah.
Okay, so we should have written that. Oh, okay.
Yeah.
Okay. Okay. I get it now. I get it. That's why. Yeah. All
So
right. Now,
even though it's 1 to 5, we say it's 5 to 1.
well, I just didn't understand what the difference between the red
Okay.
information written in red.
Well, that's
Well,
good
we put
because
200 first and 50 last, but then on the next one we actually switched it and put 50 first and 10 last. And I didn't understand that, but now I understand what you're trying to say.
and I put those two there to illustrate that point.
Yeah. Now I just didn't it didn't compute, but now it does.
Okay, good. Also, the power going to your antenna or into the feed line we call forward power, and what's coming back we call reflected.
Mm-hmm.
You don't really have to remember this formula, but it's how you actually can calculate the SWR if all you know is the forward and reflected power. So this is kind of the same stuff. High SWR is going to increase the loss in the transmission line because the voltages are higher. And the lossier the cable, the more it's going to absorb some of that reflected power. Of course, it's also absorbing your forward power going to the antenna. Okay, here's a chart showing different types of coax and what the loss is at different frequencies. And we always specify cable loss in dB per 100 feet. It's just a standard that they adopted. So you can see up here, let's look at a gigahertz. RG174 is like 1/8 inch coax cable. Would have 32 dB of loss. That's 10 to the third power. There's hardly any signal. Even when we get over to some of the bigger stuff like RG11, which is one of the half-inch 75 ohm cables, it's not what you would use in your house for TV. You normally have RG6 or RG59, excuse me, which isn't on here. And these are some like military grade numbers. And this is pretty good coax. So you can see it's still down 4 and 5 dB at a gigahertz. So in our operating range, where we're going to be in the 1 to 50, which is 6 meters, the smaller cables are going to give us, 3 to 6 dB loss. And we're still going to have a dB or so with typical cables. So the main thing to remember is it's expressed in dB per 100 feet, and the attenuation increases with frequency regardless of the cable. Wish they had put a window line on that chart, but they didn't. So remember, the characteristic impedance is determined by the distance between the centers of the conductors and the radius of the conductors for a parallel line. There's not a question about the coax, but it's the distance between the center conductor and the inside of the shield. Window line is typically 450 ohms. The transmission line is lossy. SWR will increase the loss. The more loss, the more the SWR will read low. Whenever you have a mismatch of impedance between the transmission line and the load, typically your antenna, you're going to have a reflection where part of the power is going to be reflected back 180 degrees out of phase. Feed line loss or attenuation increases as the frequency increases. Once again, decibels per 100 feet. A matching network will prevent reflected power by matching the feed point to the antenna feed point, which really means it's at the antenna between the feed line and the antenna's feed point. And you do that with things like gamma matches and beta matches, hairline matches. There's several. We don't talk about them too much, a lot more in the extra. Standing wave ratio is always the ratio of the load and feed line impedances. It's always the higher number relative to 1.
Quick question.
Okay.
The second one in red, why didn't we not write that 50-35?
Why do you not like it?
Why did we not write it 50-35? Why is it written 35-50? I thought the higher number goes first. I thought that was the whole point of my last question, was the higher number goes first.
Well, 35 is the load, the antenna, a vertical. 75 is a half-wave dipole. 50 is the feed line. So it's the ratio of the load or the antenna to the feed line impedance.
Right, but I thought you said the higher number goes first.
When you talk about SWR,
On the ratio, it goes first, not on the formula. Formula is
well,
the load
actually,
over the feed.
it
Yeah.
if you reverse this, it really wouldn't matter. You always talk about the higher number to one, whichever way you do it.
Okay, I don't understand it, but we'll move on.
Okay. Well, if I'd done this as 50 over 75,
Uh-huh.
it's going to be what? 1.5 to 1, right?
I don't know. You said the higher number goes first, and in this case, it didn't. So I'm trying to figure out why did that change?
Okay. Uh, just remember that whatever number you come up with in the ratio, whether it's 4 or 5 or 10, if it's say 1 to 10, you say it's 10 to 1 SWR.
Okay, well, I understand that part then. So it doesn't matter how the formula is written. You're saying the higher number is when you specifically write it or speak it goes first, but not necessarily the formula.
Right. And
Okay.
normally you'll just do the load to the feed line, the way
Okay.
it's written. So in most
And
cases, you're going to have a 50 ohm feed line.
this is something that we're going to have to do math wise.
Have to do what?
That mathematically they're going to give us questions that we're going to have to figure that out.
Yes, like
Okay, so
these.
I do need to understand it then.
Okay.
So
These might be the answers.
I was going to say, if you take 50 and you divide it into 30, I got 1.66. 30 divided or 0.6, which is has nothing to do with what I'm looking at. So I don't understand how to get that.
Um, I don't
If
have
I
my
take 35,
off the top of my head.
so 35 divided into, or, I'm getting 0.7. And if I switch it the other way,
Well, reciprocal of 0.7 would be 1.43.
and how do I figure that out?
Well, if you got a number less than 1, you have to take the reciprocal of it because it's got to be greater than 1.
Okay, so how do I mathematically do that? How do I do that? So I've got
Take
0.7
what?
on my calculator, and I
Take a
go, where?
reciprocal. You have a reciprocal um, key. I'm
One
looking
over
for it.
X.
And what does that look like? The little carrot? No.
Isn't 1 over X your reciprocal?
Yes. I
So
don't.
that's what you're looking for, Nanette. 1 over X on your calculator.
I
There's
don't
a
have
button.
I don't have a 1 over X.
You might have it as the
Oh,
second
I,
function on the key.
No, I've got square roots and I've got pi and I've got the little carrot, which I don't even know what that is. I have an exclamation point, tan, cos, sin, deg, inv, in, and log.
you have an x minus 1.
No, all I have is my calculator. I mean, my telephone calculator.
Oh,
I
Oh,
don't
well,
have a, what do they call that?
does it have a button for advanced?
Yeah, but I still, even in my advanced, doesn't have what you're talking about.
Really?
the
Nope.
scientific, maybe it's a scientific. You
The
have one.
scientific one, I used to have to get my kids
Well,
because they needed it.
maybe on your
I've never
scientific.
used it. Yeah, I've never used one. I've never gone that far. Okay. Because
Yeah.
I just don't know how to do all that.
Okay. Well, we'll go through it on the question.
All right.
All right. So, which of the following factors determine the characteristic impedance of a parallel conductor feed line?
Radius, the distance between the centers of the conductor and the
Wasn't it Bravo?
alpha.
Or was it Alpha?
Isn't it the radius of the conductor? It's not the length of the line.
Correct.
Oh, yeah. It was the length, the radius. Yes.
Okay.
So as you separate them, the impedance goes up. Or if you use larger conductors, the impedance goes down.
Okay.
Radius. Okay.
What's the relationship between high standing wave ratio, or SWR, and a transmission line loss?
Mhm. High WR increases the loss.
Correct. So it'd be
Bravo.
Bravo. Yeah.
What is the nominal characteristic impedance of window line transmission line?
That's your 450 that you said,
Yes.
delta.
The window. Yes.
What causes reflected power at an antenna's feed point? That's where you actually connect to the antenna.
Charlie.
Charlie.
Charlie. How does the attenuation of coaxial cable change with increasing frequency?
Goes up. So Bravo.
Bravo. Yeah.
In what units is RF feed line loss usually expressed?
DB.
Guess for
So,
100.
per
So
100.
delta.
Delta. Yeah.
What must be done to prevent standing waves on a feed line connected to an antenna?
Delta.
Delta.
Delta. If the SWR on an antenna feed line is 5:1, and a matching network at the transmitter end of the feed line is adjusted to present a 1:1 SWR to the transmitter, what is the resulting SWR on the feed line? It's kind of a trick question.
Yeah, because it says it in the first sentence. The SWR on the antenna feed line is
Feed line's 5:1. Right. So that's Bravo, right?
Right.
Yeah. Okay.
The point is, it doesn't matter what your matching network at the transmitter does. That's only what the transmitter sees. It doesn't affect the feed line.
Right.
What standing wave ratio results from connecting a 50 ohm feed line to a 200 ohm resistive load?
It's a quarter. And a quarter over.
See, here's where that math comes in.
You can do this in your head.
Shoot.
So it would be a quarter, but you do the high number first, so that's 4-1.
Let's see,
Right.
I don't even know where to start with that. So that's what I was saying. I don't know what to do with it.
So isn't that just the 50 divided by the 200, or have I got that backwards and I just lucked out?
Okay, so if I took 200,
200 divided by 50.
50 is
Yeah,
4.
it's the quarter.
4.
So it's 4-1. Okay.
Okay, well, there's the formula.
Okay.
And I think let's remember it this way. You take the high divided by the low.
Yeah, that's what I was just telling myself. That's exactly what I came up with.
What standing ratio results from connecting a 50 ohm feed line to a 10 ohm resistive load?
All right.
And this might help, right? Because you can throw out Bravo and Charlie right off,
Right.
right?
So
Because they're not over 1.
it's going to be Alpha.
So it's either alpha or delta, and 50 divided by the 10 gives you the
Oh, because when you write it,
delta.
when you write it, you put the higher number first. Well, no,
Right.
that's no, but I didn't get a 5, so I got a 2. So it has to be alpha.
Oh, well, then
Wait,
I think it's delta.
Is that right?
well, remember the previous one, Z high divided by Z low.
All right, so
What's Z high?
50,
50. What's Z low?
10. So I'm going to take
So
50 and
that's
divide it
5,
by 2.
right?
Oh, I did it backwards. Okay, yes, you're correct. Delta.
It wasn't that hard, was it?
Well, I'm just going to have to practice where my numbers go. That's my big key.
Okay. What's the effect of transmission line loss on SWR measured at the input to the line?
What is the effect of transmission line loss on endpoint to the line? It
Higher loss reduces SW.
right.
So
I thought,
alpha for me. I'll
yeah,
try.
alpha. Higher loss reduces your yes.
Let's see. And the answer totally
Yes. All
correct.
right. Good.
Yeah, if you look at Charlie, they tried to fool you. So they say increases.
Yeah. They don't really have to do these trick questions.
Right.
It's
They're
not necessary.
right. It's enough as it is. Yeah.
Yeah.
What is the interaction between high standing wave ratio and transmission line loss?
Hmm. Transmission line is lossy. Bravo.
Correct. Yeah. The higher the SWR will increase the loss. Yes.
What's the effect of transmission line loss on SWR measured at the input to the line?
What is the effect of transmission?
It's very similar to the other question.
Down. So it's not affect. No.
It's going to be alpha.
Higher transmission line, the more.
That's the one you were saying you can't trust it.
Right.
Yeah, that's right.
Okay. Very
Oh
good.
my gosh. And this is why I haven't just dived in and buried myself in it. Oh my gosh. Okay. Don't forget to stop your recording.
Um, oh, there we go.